Last week we learned to calculate confidence intervals. What did we do with those confidence intervals? Well, we had a population from which we drew a sample. We then looked at one of those sample parameters, either the mean or a proportion, and we wanted to draw conclusions from that sample about the population. Now, if you're already getting lost talking about sample and population, you need to stop the video now and you need to back up. You need to pull out your textbook and make sure you know the difference between population and sample, because it's critical to last week's work and this week's work and week 8's work. Lost my place there. Okay, so confidence interval. We have a sample that we've drawn from the population. We've calculated some parameter, let's say the mean. And now we want to draw or calculate what's called a confidence interval. And from that confidence interval, we can say we are confident at such and such a level, the 95% level or the 90% level. We are confident that the true population mean falls within our confidence interval. It's a common technique. It's a powerful technique. And it's used by statisticians quite often when drawing a sample and making statements about one of several population parameters, the mean and proportion being the two most common. Well, this week we're going to extend that work a little. Our work is quite similar. We are not going to calculate confidence intervals. Actually, I guess we are in our CT work, but that's a minor part of it. What we're doing is looking at, again, making statements about the population based on a sample that we draw from the population. So that's where there's similarities. We're going to be looking at means of our samples. We're going to be calculating the standard deviation of our sample. And we'll be making statements from those parameters about the population, just as we did in week 6. The calculations, again, are not very difficult. They can be done by hand, but we will be doing them on the computer as well. Once again, just like last week, it's kind of neat to check your work. Do it by hand, and then let the computer do the work and see if we get the same numbers. Okay, what we're learning this week, we are calling hypothesis testing. Hypothesis testing. And in hypothesis testing, it begins with a hypothesis that we call the null hypothesis. Null hypothesis. Well, we actually have a second hypothesis, which some authors use H sub 1, some use H sub A. Our author uses H sub 1. It's called the alternative hypothesis. And what we're trying to do with hypothesis testing is to either accept or reject the null hypothesis. And let's just look at a simple example. Let's say my null hypothesis is that the mean is equal to 25 miles per hour. And the alternative hypothesis then would be that the population mean is not equal to 25 miles per hour. Pretty simple. We're trying to prove or disprove the null hypothesis. We're going to draw a sample from the population of values, and they must be the speed of some vehicle, probably a car, and we're going to calculate a sample mean. We're going to calculate a sample standard deviation, and then we're going to look at the software will do it for us. We are going to either decide that we can accept the null hypothesis or reject it. That's what it's all about. We're going to look at doing this a couple different ways. the second part where we are looking at the p-value, it's called, is the one that we'll use in our critical thinking assignment, and I'll concentrate on that one. But first, let's talk a little bit more about this hypothesis testing technique. Whoa, losing it. Okay, once again, I apologize. We are going to be using a couple different data distributions. We will be using the normal distribution, where we will have our z-score. We will also be using the t-distribution. And last week, several of us got a little bit turned around on that, and I'll be talking about a table in the book in just a little bit later. But when we know the population standard deviation, we can use the normal distribution and calculate the z-score. However, if we do not have the population standard deviation, well, then we're just going to have to calculate the sample standard deviation from the sample we draw, and we'll be using the t-score in that case. Big difference. Only one way to do it. If we have the population standard deviation, that's rare, then we can do it the simpler way and the more assured way using the z-score, the normal distribution. However, most cases, we won't have the population standard deviation. We'll have to calculate the sample standard deviation, and then we will use the t-score. I've drawn a distribution, and I haven't said which one it is here. It doesn't really matter. But the point is, we are going to calculate a score, a test statistic. Could be z, could be t, and it's going to fall somewhere. Let's see, let's call that our calculated stat. We'll just call it that. And we're going to have, in the example like the one that I began, where the null hypothesis was that the population mean is 25, we are going to have an area where we accept H0, and that would be that big area here in the middle. And we're going to have two areas where we're going to reject H0 and conclude that the alternative hypothesis is correct. Those would be the ends of the distribution. One thing you are asked to do in our discussion board this week is to describe a situation in your life in terms of the null hypothesis and the alternative hypothesis, and then also describe in which cases you might accept or reject the null hypothesis, and I guess you could also talk about what would be the results of that. I'll come back to that in a minute, but first of all, I want to talk about a table. It's table 10.2 in your text, and I've redrawn it here. Again, H0 is our null hypothesis, and the purpose of calculating hypothesis testing is either to accept or reject the null hypothesis. Now, here's where it gets a little tricky. First of all, we have to assume that the null hypothesis, first of all, first let's assume that the null hypothesis is really, truly correct. That's this first column here. H0 is really correct. Yes, it is. Well, in that case, again, remember, we're trying to accept or reject the null hypothesis. But if, we don't know this yet, but if the truth was that it really is correct, that we should be accepting it, and we do accept it, we've done the right thing. We've made the correct decision. Yay us. But you know what? We might not make the right decision because statistics aren't perfect. There's variability when you're drawing a sample from the population. And if we reject the null hypothesis, hypothesis when truthfully, really, yes, it was correct. We've made the incorrect decision. And doing so has a name. We say we've made a type 1 error. Okay? Now let's turn it around. Let's say H0 is really false. We're doing our stats. We're going to try to determine whether to accept or reject it. But we don't know this, but it truly, really is false. Well, what happens if we accept it? It's an incorrect decision, of course. It also has a fancy name. Doing so is called making a type 2 error. Type 2. Finally, the fourth quadrant here, the null hypothesis is truthfully false, and if we reject it, well, again, we've made the correct decision. We rejected it. We didn't know it, but it really truly was false. And we call this the power of the test. Let's see. Or the probability, which we're not going to learn much about, 1 minus beta is termed power of the test. I left off one piece. If the null hypothesis truly is correct and we reject it, we know that that's an incorrect decision, and that's going to occur alpha times, where alpha is our significance level. We might be looking at a 0.05 significance level, which corresponds with our confidence intervals of a 95% confidence level. They kind of turn them around in the two. You'll see why a little bit later. Okay, let's talk about, let's make it up an example so you guys can get to that discussion board. I am thinking of moving across the state to my hometown sometime later this year, maybe next year, I don't know. But I have to make an informed decision, and so I'm thinking that there are many jobs in Madison where I want to move. Sorry, we're falling off here. The alternative is that there are not many jobs. I'm hoping my null hypothesis is correct, because if I can find work in Madison, I'll be successful there, and it won't be a poor decision to move to Madison. So here's a personal decision on my part, and we can kind of write it. It's a little bit hokey, but in terms of the null and the alternative hypothesis, I will be successful if, and I'm hypothesizing that there are many jobs in Madison. If we end up rejecting the null hypothesis and accepting the alternative hypothesis, well, that means there were not many jobs and things aren't looking too good for dear old Craig. Okay, so how are we going to put this in terms of the type 1 and type 2 errors? Well, let's see. A type 1 error occurs when H0 is really correct, but we accidentally reject it. And so how would that come to be in this silly little example. There were many jobs in Madison, but for some reason, I reject that fact. I determine that there's not so many jobs when truly there were a lot of jobs. That would be the type 1 error. I decided there were not many jobs. I rejected the null hypothesis. Likewise, what's an example of the type 2 error in this scenario? Well, a type 2 error is when the null hypothesis is actually truly false, but we accept it anyway. So in my case, my null hypothesis is that there are many jobs. Well, now we know for a fact that that's really false, that there's not many jobs. And yet I don't know that because this is a hypothesis test. And I accept the fact. I believe there are many jobs when truly there are not many jobs in Madison. That would be my type 2 error. Believing that there's many jobs in Madison when in truth there are not many. All right, I'll be curious to see what sort of examples you guys come up with and what your interpretation is of that. Earlier, I drew this diagram, and I told you that the method we are going to use in this chapter to either accept or reject the null hypothesis was to do as we've done in the past. We are going to calculate either a z-score or a t-score, and we're going to look at our distribution, our normal distribution, or our t-distribution, and we're going to compare at some level of significance where our calculated value falls. And based on that, we are either going to reject or accept the null hypothesis. Well, that's one tack to take. You establish your confidence level, you calculate your test statistic, and you compare the two. Well, what if we do something slightly different? What if we calculate what this proportion is? Basically, we're calculating what the area is under the curve at our z or t-score. We call that value the p-value. And basically, the p-value gives us the level of significance. It is the lowest level of significance at which we can reject the null hypothesis. I'm going to do an example for you in just a minute, but first of all, once we've calculated the p-value, again, it's giving us a level of significance at which point we can accept or reject the null hypothesis. Now, we're going to be doing it by hand, but we'll also be doing these via computer. And we need a hard and fast rule for knowing how to interpret p-values, and here it is. This is from page 326. If our p-value is less than our significance level, and our significance level is going to be 0.05 or 0.02 or 0.01, something like that. If it's less than the significance level, then yes, we will reject H0. But if it's not, then we will accept the null hypothesis.